Right. So as people will slowly filter in as their reminders remind them of the time, I'll start by slowly flipping through the IRTF note well, though. So welcome to everybody who's already joined. So I do want to draw attention of everybody who has joined to actually pay attention to the slides on the screen. And if you're not on the slide view, you need to click on presentation mode on the top screen, as the note well does contain just admin stuff we need to tell you about. And as the last slide of the note, well, just a reminder that IRTF, for those, hopefully most of you will know, it is an organization to conduct research. It's about forming collaborations, and we're not about standardization like the IETF, our sister organization. And with that, the note well out of the way, I'm going to close this. I would like to introduce our speaker, Wolfgang Durr. So Wolfgang is an associate professor at the University of Innsbruck. Works on all aspects of quantum information theory and has contributed to various topics across quantum networks, metrology, measurement-based quantum computing, decoherence, and large-scale entanglement, and multi-part entanglement especially. During his master thesis, he has co-invented the quantum repeater, which hopefully most people in this should be aware of. And he has worked a lot on multi-part entanglement. But rather actually than me talking a lot about Wolfgang, I will let him talk about his work. So I will now hand over to Wolfgang. And thanks for agreeing to this meeting. Is there an issue with the screen share, though, it seems?
I have a screen sharing issue, yeah. Before it worked, now I ask for permission and it
doesn't.
I say yes, and okay, no.
So you can always just do the pre-shared slides. They're uploaded already.
I just switch to the pre-shared slides then. So I also have to ask for permission for this. So okay.
Okay, I'll let you.
So,
thank you, Wolfgang. I'll hand over to you now.
Okay, well, thanks a lot.
Actually, sorry, just one more thing. Wolfgang, you're okay with people asking questions during the talk as well?
Yes, that's completely fine. Just interrupt me. It's better that you understand something and I don't get to the end and that you don't fall asleep. Okay. Well, thanks a lot for the kind invitation. I'm really happy to have the opportunity to present some of the results we obtained in the last couple of years in my working group here at the University of Innsbruck. Well, these results are mainly together with Jorge Miguel Ramiro, who is still a PhD student with me, with Alexander Pelka, who finished his PhD, is now earning real money, and with Ferran Sabat, and to some extent Julius Wallner, who is now in Berlin, is also involved. So the title of the talk, which I think was actually never really advertised, is Genuinely Optimized Entanglement-Based Quantum Networks. So what I want to do today is really trying to convince you that entanglement-based networks really give you some more opportunities than the standard way of thinking about quantum networks. And on the other hand, I would try to convince you that we are not really yet at the most general level. So we can really try to make the quantum networks a little bit more general by essentially having a quantum control plane rather than a classical control plane. So that's the overview. So I will first start with a very basic introduction, motivation about entanglement and how to use it, why we really want to have a network. I will tell you about what we understand under an entanglement-based quantum network, and in particular, that you can actually optimize these networks independent of the real physical structure of your underlying physical network. Then I will show you how to really make your quantum networks genuine quantum. And then if I have time, but this is flexible, I can tell you about some other relevant network protocols for long-range communication, some bits and pieces where we try to contribute to this. Okay, let me start with introduction. So if you look at the classical system, then the bit is sort of the basic unit of information. The classical bit has a value 0 or 1. And well, that's about it. You can manipulate this bit, you can store it, and everything we do when using a computer or sending information through the internet is exchanging and manipulating bits. Now, in the quantum world, things are a little bit more complicated or different, but that's what makes things exciting. Namely, that these, if you look at the simplest quantum version of the bit, the qubit, it's not only in the state 0 or 1, but it can be in sort of a kind of superposition of both at the same time with different weights. And actually there's also a phase involved, but that's not so important. But the important thing is that now we have superpositions of different states, not just the basis states. We can sort of represent this by the Bloch sphere, by a vector pointing in one direction in the space of R3. And this vector can point actually not only up and down, which would correspond to the classical bit values, but in any direction. So it can be in any superposition of the state 0 and 1. And this superposition actually makes up what is the true power of quantum physics. Because if you extend this basic principle of a single qubit to more complicated systems like 2 qubits, now you encounter that there are superpositions of states which have a form like this one, which I'm showing down here, is psi plus, which is a 0, 1 plus 1, 0. And these kind of superposition states, they are called entangled states. And these entangled states, they have very nice features and counterintuitive features. If you do measurements on them, for a single qubit, you get a completely random outcome independent of what measurement you do. But if you do a measurement on the other particle as well, in the same basis, then you find that the results are either correlated or anti-correlated, depending on which measurement basis you're using. And what we've learned in the last couple of years or decade is that these entangled states, they are not only fancy and have some sort of weird features, but they can act as a resource. We can do something meaningful and powerful with this kind of states. And well, that's just to complete this. There's a nice picture to visualize an entangled state, namely the singlet state. We can visualize it as a rotating coin, where sort of the state of each system is not yet defined. But once you stop the coin to rotate, which corresponds to doing a measurement, and then you look to the coin from one side. This is what Alice does. One party does, and the other party looks at the coin from the other side. Then these measurement outcomes, what you see as a measurement value, they are really complementary. You get a different outcome. So whenever one sees head, the other one sees tails. And this is a picture which was coined by a colleague of mine from didactics, but which I find very nice to understand what entanglement is, well, it's quite nice to use this at school, at high school, for instance. Okay, but anyway, coming back to these applications of these entangled states, well, there's or what Einstein called something like a spooky action at the distance. If you do a measurement on one side of an entangled state, you can sort of enforce the other particle at the other side to show, to point in a specific direction. But one has to be careful. It's like it's somehow a remote state preparation, but not completely. So you can only choose the direction, but you cannot choose whether the state is showing up or down. So you can sort of choose the basis, whether you want the Z basis or the X basis, but you cannot choose the result of the measurement, and you cannot choose whether it should be the 0 or the 1 state. So this is not useful for communication without any sort of classical side channel. But if you got this as well, then you can do our most favorite thing in the quantum networks business, namely teleportation, that we can transmit unknown quantum information. So an entangled state is a resource for communicating the state of an unknown qubit, but that's sort of not coming for free. On the one hand, you need this entangled state, and you have to prepare it beforehand, but once you have it, you can communicate whatever other state you have. And on the other hand, you need some classical side channel. You need some 2 extra bits of classical information in order to complete the teleportation process. And that's crucial, that we have to keep in mind that when we talk about quantum communication channels and quantum networks, we always have sort of an underlying classical network as well. Okay. But throughout all the talk, what I consider is that this classical communication is cheap. And we can do it. We can do it fast. We can do it without problems. And the quantum communication, that's actually the hub. So I will concentrate on the quantum communication. So this was about 2 qubits, an entangled states of 2 qubits. But if you have more systems, several qubits, there are other interesting entangled states which you can have. And one interesting entangled state, of particular interest, is the so-called GHZ state, depicted by this sort of spider. So the second plot here, because I guess you cannot see my pointer, and I don't know how to get one, but anyway. Okay, so this GHZ state is a sort of a generalization of a Bell state, where either all qubits are in state 0 or all qubits are in state 1. So all of these particles are correlated with each other. And it's sort of a toy example of a Schrödinger cat, if you wish. And this GHZ state, this has many other applications. I will come to this shortly. And this is a special case of a larger class of interesting multi-party entangled states, which are called graph states. And these graph states, this is what I will talk about throughout most of this talk. And these graph states, they are defined as a class of multi-party entangled states associated with mathematical graphs. So you have a set of vertices connected by edges. And to each graph, you can associate a state by just saying, whenever I have an edge, I have an entangling gate between these particles. That's the first definition of these graph states. But equivalently, you can describe these graph states in terms of correlation operators. So they are joint eigenstates of correlation operators, which are just defined by putting an X on a vertex and Z on all the neighbors, on all qubits which are connected. And in this way, you really define uniquely a class of states which corresponds to all possible graphs. Now, the nice thing with these graph states is that in contrast to general states, you can actually describe these states efficiently, and you can prepare these states efficiently. Because if you look at the general multi-party state, you have exponentially many coefficients, and it's usually very hard to describe these states. But the graph states, you can describe efficiently, and you can prepare efficiently. And the even nicer thing is that there are many examples of interesting states which are in this class of graph states, like code words for error correcting codes, like these GHZ states, which are resources for metrology, like this 2D cluster state, which is a resource for one-way quantum computation, and so on and so forth. Now, these graph states, you can actually manipulate them as well. You can erase certain vertices by doing a Z measurement. You can join different graphs by merging vertices. And you can change the graph by doing a so-called local complementation of the neighborhood graph. So there are ways how you can modify the structure of your state by just doing local operations. And actually, I've sort of summarized some things you can do. So if you start with 2, if you look to the top, if you start with 2 different graphs, this would correspond to sort of code words for error correcting codes. You can actually merge them together such that they form a joint graph. Now, the second example, this is the GHZ state example. And what you can do from a GHZ state by measuring all but two particles, you can actually prepare a belt state between these two particles. And you can choose which of the particles should share a belt state. So you have some flexibility in sort of sharing different kinds of entanglement if you start with the belt state. And a generalization of this is a graph state of 6-qubit butterfly state, it's called, from which you can actually produce two belt states shared between any two of these red particles. So all these different configurations. And more generally, if you have a 2D cluster state, you can actually go to any graph state just by doing local measurements. You can do this deterministically. And this is what is called one-way or measurement-based quantum computation, a thing which was coined by or introduced by Kriegel and Rausendorf quite some time ago. But sort of what you need is a little bit, or is a larger 2D cluster state, so a graph state corresponding to a rectangular lattice. And from there, by just doing measurements on the particles and by choosing the proper measurement bases, you can choose which other state you want to produce. Okay, why I'm telling you all this? Well, on the one hand, we want to sort of generate these graph states. I'm trying to say, okay, well, they are important. They are quite general, and there are many, many interesting applications you can do with them. So if we talk about a quantum network, we actually would like to share that this network can produce these graph states, that the parties, the nodes in the network can do interesting things with these graph states. And what you can do with these entangled states, one thing is teleportation, I already mentioned, but even more importantly is the quantum key distribution or quantum key enhancement, actually. Also that you can do secure communication, you do cryptography based on these entangled states, or by sending quantum information, both things work. You can actually generate these different multipartite graph states, and the GHZ states and other graph states, you can use them for secret sharing, secret voting, some conference key agreement, some secure multi-party applications. More from a physical perspective, what is also nice is that you can use GHZ states for clock synchronization, that you can synchronize different atomic clocks. You can actually enhance the accuracy of distributed clocks. You can use this for metrology. So quantum metrology, that's the science of doing measurements, precise measurements. And if you are interested, for instance, to measure the Earth's magnetic field or the Earth's gravitational field, and you're not interested in just the field at a certain position, but at different positions, then if you distribute certain entangled states, some GHZ type states or others, then you can actually do these kinds of measurements with help of these distributed multi-party entangled states with an increased accuracy. So you can actually sort of choose the internal states of your sensors, which are at different positions, in such a way that you can choose which quantity you want to measure, whether you want to measure sort of the zeroth moment of a field, or you want to measure the gradient, or you want to measure some Fourier coefficients. You can choose by choosing your state what you want to measure, and actually by using these quantum entangled states, you can do this in a more accurate way. And last but not least is distributed quantum computation, because nowadays we are talking about having available some small-scale quantum processors, but in this NISQ area, with these noisy intermediate-scale quantum devices, these processors, they won't be very large. So with these current setups, we can expect something like 10, 20 qubits, maybe 50. But it's not so easy for some of the setups to scale this up to huge systems. But if you have several copies somehow of these setups, several small quantum processors, well, if you only have them disconnected, that's not very powerful. Actually, it's like having m copies of something, and sort of the computational power is m times the one of the individual one. But if you manage to connect them, to connect these distributed processors, and they can be at different positions in the same lab, or they can really be distributed among several cities or among the whole Earth. Then if you do this, then you actually get a quantum processor which consists of the sum of all these qubits. And this is actually exponentially more powerful than the individual ones. Okay, so also from this perspective, to connect these quantum devices, to connect the quantum processors, that's also an interesting thing. Okay. Now let me come to these entanglement-based networks. So if you think of the standard way of quantum networks, so the way you probably think about the quantum networks, you will have quantum devices which are connected by channels, and the goal is then to transmit quantum information between these devices or to prepare some entangled states, which is sort of equivalent. And the usual approach is that you have a classical control plane, which sort of orchestrates everything, and this classical control plane, this controls the quantum devices. And then you have to design a protocol to distribute your entanglement and to utilize it. And the main problems in this context are the routing of entanglement, how you get in a given network that you share entanglement between some given two parties, and how to do this over a long distance. And quantum repeaters, this is actually something or a way to overcome channel noise and a way to overcome the no cloning theorem, if you want to say so, which is basically or one variant of the quantum repeater that we introduced some long time ago, actually during my master's thesis, is sort of based on entanglement, that you purify entanglement by having several copies of noisy entangled states. You can sort of distill the entanglement into fewer copies, and if you connect then these sort of short distance pairs of high fidelity still, the fidelity decreases, but then you can repeat the process with the longer distance pairs, and you get sort of a nested loop of this kind, and one can actually show that this is an efficient way of generating entanglement over long distance and then via teleportation to ensure quantum communication. But what I want to convince you today is that a quantum network is more than just a variant of a classical network that transmits quantum information rather than classical information. And but okay, I think basically I said this, so that the bottom-up approach is the usual approach. You generate entanglement between end nodes. This is similar as in classical networks. You receive some requests. Parties A and B say, well, we want to talk to each other. Please provide us with some entangled states. And these parties, they are connected via different channels and via some intermediate nodes. And then you have to cook up a protocol how to generate this entanglement via different passes or whatever. I don't want to go into the detail. But what you should bear in mind, that this process of generating entanglement, doing this over longer distances, and really sort of establishing an entangled link between two parties, that's way more complicated than just doing classical communication between the two. Because for classical communication, you just send things along, and noise doesn't really harm you very much. And you don't have to worry about this. There are several passes which you can use. It's just that some package eventually needs to appear at the side B, and that's sort of already achieves your communication. Well, with the quantum systems, it's way more complicated. There's a huge overhead in resources which you have to use. You have to use the noisy channel several times if you want to run then this entanglement purification and get high fidelities. And also you need several rounds of classical communication to make sure that actually the qubit you send arrived on the other side, or that your entanglement purification step succeeded. So bear in mind that there's a huge overhead to obtain these entangled states. And so if there is some request, some quantum request on your network, then actually you will have to wait for quite some time before your network, your underlying physical network, manages to establish your entangled link, say between here, Innsbruck, and say Sydney or New York, some very far away cities. Okay, so that's the bottom-up or the usual approach, I would say. And of course, there's been many attempts to design protocols there. Many people here, the Delft group, but also Rodney, they contributed significantly to this. Okay, but what we said is, well, let's take a different angle, take a different point of view, make a top-down approach, which is sort of inspired by this measurement-based computation, namely work with entanglement as a resource. And we sort of cook up our network or our entanglement-based network by 3 phases. The first phase is really generating certain multi-party entangled resource states. And well, this is essentially the same as what is done in the standard network, with the difference that we know which state we want to get, and we know beforehand. We know from the very beginning which states we want to generate. And we can do this not when a request comes in, but already before. We can sort of, when the network lies idle, we can use it to establish certain entangled states. So there's no time pressure for this. And then we enter the static phase. So these entangled states, they have been distributed among the nodes, the nodes or the components of the network. And then they are just maintained and stored. So you need a long-term quantum memory to achieve this. But actually, to establish long-distance quantum communication, you already need a quantum memory. It's not just a big deal to have this quantum memory available for longer times. And even if it's just working for some time, okay, you can refresh the resources which you have. Okay, but in the static phase, essentially you just store and maintain the entangled states, well, unless you get some network failures, some devices drop out or log in, and then you have to update your network state. So the resource state which you want to share. Because of course you want also new devices to participate in any other protocol. Well, and then the final state is the adaptive phase. And in this adaptive phase, what you do is you manipulate your entangled resource state, which you choose properly at the beginning, such that you generate the desired target state. So here is when now the request enters. So this is the phase 1 and phase 2 we did beforehand. And now comes a request. Now particles, now some two nodes say, I want to share a Bell state, or I want to share a GHZ state with these other two parties. And once this request comes, the only thing you need to do is adapt your stored entangled state, you manipulate your stored entangled state just by local operations, local measurements, and some classical communication. And you can, if you have chosen the state properly, you can actually get the desired target state basically right away. You only need one round of classical communication saying where everybody says, well, this was the measurement outcome I got. And then the target parties can just do some correction operations as in teleportation, and they share the desired target state. You don't have to use your quantum channels anymore at this stage. And that's why this approach is really fast then at this stage. Of course, for building up the entanglement, you essentially have to do the same work as before, but once you need it, you don't have to start from scratch, you have it already pre-prepared. And I should emphasize, while sort of this top-down approach is something like an extreme case, of course you can think of hybrid schemes where you just share a few copies of some entanglement in such a way that you can speed up the process for providing the quantum communication. So it's not that a must that you do it everything in this way. Okay. So another interesting thing is that now this topology of this entanglement-based network, this is sort of given by the entanglement structure of your shared state. And this is independent of the underlying physical network. So you can build sort of your own optimized network on top of your physical network. And you can design it in such a way that the requests of the network, the functionality of the network, is sort of fulfilled by your resource state. It can be fulfilled without delay, that's what I said already. But the question, one of the questions, which resource state should we store? What are good resource states? And of course, if you just stare Bell states between all pairs of nodes or all pairs of devices in your network, well, that does the job, of course, because you can use these Bell pairs for teleportation, you can merge them together to form graph states, you can basically manipulate them. But if you look at this from a storage perspective, well, every node has to store a lot of different Bell pairs. And that's actually quite wasteful. And you can do better by choosing proper multi-partnered entangled states, then they allow you for a storage advantage. And let me just try to sort of show this a little bit. If you have a 4-node network, and the goal is to generate an arbitrary graph states between these 4 nodes, you can either do this by sharing entangled pairs between every pair of qubits, or between all the different nodes. And this, in total, takes you something like 12 particles to store. Now, you can achieve the same functionality by GHZ states, a GHZ states of size 4, a GHZ states of size 3, the green one, and the Bell pair. And with this, you have a little bit less resources. It's 7 qubits only which you need to store. Or you can also achieve the same functionality by a so-called decorated graph states, where you take a fully connected graph and you put an additional qubit or vertex on each edge. And this one allows you then to decide for each edge by measuring this out either in the Z or in the Y basis, whether you want to have this edge, if you measure in the Y basis, or you don't want to have this edge, you erase it, and then you do the measurement in the Z basis. All of these states, they allow you for this full functionality, but they are sort of made up of different resources. And then the question is, what are the best ones, which give you the minimal error, which give you the minimal storage requirement. And that's what we concentrated on. When I talk about optimality, I will talk about the sort of the storage requirement. I don't worry about noise at the moment, but of course one has to take this into account as well. Well, for these entanglement-based networks, we actually came up with a stack model similar to the OSI model. We have a physical layer, you have a connectivity layer, a link layer, and a network layer, where you have sort of devices, quantum devices associated to the different layers. The physical layers have the channel. At the connectivity layer, you have a repeater to establish high fidelity entanglement. The link layer are switches, or quantum switches, and in order to connect different networks, you have a router, and then of course there are different protocols, how to establish these entangled states and how you would manipulate them in order to get the desired target configuration. Say if there comes a request that one node in one network wants to share an entangled state with another node in another network, then you have to sort of manipulate these resource states, which you have to design, of course, first, in order to get these entangled states. And these are things what we did in this paper together with Alex Birker. And I won't go into details with this. I just flash that there are different network devices. There are resource states. You can try to optimize them. You can design protocols to generate these states, to transform these network states to the desired target states, a state linking protocol, region routing, and so on and so forth. And there are also methods to ensure reliability. Maybe I will say a little bit about this. This is just a graphic representation of this, where you have sort of three routers, which are sort of form three different, it's one network consisting of three routers and one switch, and they are connected by physical channels, which are these orange tubes. And there is entangled states shared inside these routers and the switches in order to ensure their functionality, and there are entangled states shared between the different devices. And one thing I want to point you to is that if you look at the connectivity in physical terms, which are the orange tubes, this connectivity is different than the entanglement structure of the states issue. I will come back to this later. Okay, I will skip this example. I'm running out of already late a little bit. Regarding the reliability, one problem you have if you share these entangled states is that they are actually very susceptible to noise. So if you take a GHZ state and you lose one of the nodes disconnects, or one particle gets lost, then the whole GHZ state is destroyed. So if you really share a big GHZ state among several parties, then by just losing one of the nodes, everything is gone. So you have to think about strategies how to protect this. And depending on which of the nodes, if you take this sort of universal structure with different sized GHZ states, depending on which of the nodes loses a particle, either your whole entanglement can be destroyed or only part of it. And you can sort of use this by doing a symmetrized version of this protocol in order to protect more parts of your entangled states, or you can actually add some shield particles, in the sense that if one of the nodes disconnect, other parties hold an extra qubit, which they can sort of measure then in order to disconnect this other node in a controlled way, even afterwards, even after the particle is lost and the remaining entanglement stays intact. Okay, but let me switch to these optimized networks, to really cooking up your own entangled network and sort of constructing this in an optimal way. This is a work with Alex and Jorge. And what I want to emphasize is that usually in a standard network, the channels are just given. You have nodes at certain sites, and they are connected by some cables or by some channels. And there's not much you can do. You can maybe put some extra router or some extra switch, but usually the physical structure of this network is given, and you just have to work with it. And if there is a bottleneck in the network, if you really want to communicate from one side to a far away side, and if there is sort of only a small link which is used heavily, then this is really sort of restricting your communication. There's no way around this. You have to build some extra physical channel, and this might be complicated. On the other hand, if you just want to share some entangled states, you can actually choose which entangled states to share. So you can just say, well, I take these parties A, B, and C, and I decide these three, they should share an entangled state. And I choose this because I know that these three parties, they tend to talk a lot to each other, so I better have some entangled states prepared for them. So actually what you can do is you can optimize the geometry of your entanglement-based network in such a way that you minimize storage requirements and guarantee the functionality of the network. Okay. Now, the way we think about this quantum network then is that there is a certain set of functionalities this network should fulfill. You have these end users in there, these nodes in there, and they want to share some entangled states. User 1 wants to share an entangled state with user 7, and that's one use case, or one possible functionality. But it can also happen that two of the users want to share an entangled state. And there are sort of a bunch of possibilities, and each of them can be described again by a graph or a graph state if you wish. And all these functionalities, this should be guaranteed. So the functionality of the network is sort of given by a set of graph states with certain probabilities. The probabilities that this particular use case or this particular functionality is requested. And this sort of makes up what this, or defines what this quantum network should do. And in principle, from previous data analysis, you can already determine what is your expected sort of target configurations or quantum communication going on the network. Okay. And what we are interested in is that for a given functionality, what is the minimal resource state to guarantee this functionality, either deterministically, that each of the use cases can be fulfilled, or sort of corresponding to these different possibilities if you talk about the multi-copy regime. But let me stick to the deterministic regime, where you say, okay, all use cases are equally likely, and we just have different target configurations. But what we can do is we can adjust the topology of our network to the desired target configuration. And recall, we had two tricks of reducing the size. Namely, one trick, or there are more actually, we came up with another one. But the first trick is to say, well, the GHZ state is actually a resource which can guarantee me a single quantum channel between any two particles in there. And this really saves a lot of resources if you don't know beforehand which of the two parties want to communicate. And it's just one communication you want to guarantee. And on the other hand, the 6-qubit butterfly state, this can actually guarantee two parallel communications, sharing two parallel pairs between two different pairs of nodes. And this has been considered by Rodney and also Jens Eisert. But you can sort of generalize this state to larger systems, and what you see is that actually you can save a lot of particles if you really do it like this. So our approach really consists in two steps. We first analyze sort of our network, our desired functionality, via clustering algorithms. You really want to identify which nodes in the network do heavily communicate and which nodes are more or less separated. And for this, you can actually use classical clustering. You just have to come up with the appropriate matrix, the cumulative matrix, which sort of gives you the number of links, the number of times a link appears. And from there, you can do a clustering algorithm and identify sort of nodes in the network which have high traffic and nodes in the network which have lower traffic. And this really gives you the different regions in your network which you sort of connect with each other. So somehow this procedure gives you the topology of this entanglement-based network, because you make that these highly connected qubits, they share entangled states of a specific kind. And you can actually do this in a hierarchical way, that you can then, within sort of one of these heavily used networks, you can sort of say, I take a router which represents this network, and then make the same clustering algorithm at the next level. You can do a hierarchic clustering and then sort of a hierarchic construction of this resource. Okay, that's one thing. And then you just put bell states wherever you need them. And then the second thing is then that you try to sort of reduce these bell states to multi-party entangled states. And this is what we do by a merging algorithm, which basically tries to, rather than having two independent bell states, try to really join them together. Like if you go back, if I go back to this GHZ example, if I have all these different functionalities which I desire, that you have all these different bell pairs, well, actually the clustering algorithm constructs out of this GHZ state, which gives me the same functionality. And well, these plots, they just show that this actually works very well. If you look at the bell state approach, so on the y-axis is the total number of qubits you need to store, and on the x-axis is the number of network nodes, and then we put a sort of randomly chosen target configurations and of different kinds. So that's why we have many different plots corresponding to different types of networks, essentially. And if you look at the curves for the GHZ states, for the bell states, well, actually the resource requirements, they sort of scale quadratically with the number of network nodes. Well, if you do the clustering and merging approach, this is the green curve, the lowest one, you really save a significant amount of memory. So you don't need to store that many qubits. Okay, and depending on the target structure or the structure of the target states, this can be even more enhanced if you look at the top curves. Okay, now let me switch gears a little bit and sort of leave these entanglement-based networks, because what I have to say now also applies to the sort of standard bottom-up networks. And come to this, what we call genuine quantum networks. So the idea here is that you perform the different tasks in the network. So the state generation, the state manipulation, the sending, the addressing, not sort of in a classical controlled way, but in a quantum controlled way. That you can do everything there in...
Wolfgang, can I pause you? I think Tobias has a question.
Oh, okay, sorry, I didn't see this.
Yeah. So I'm kind of bringing that. Tobias, do you have a question? Would you like to ask it?
Yes, if you can hear me.
Yeah.
Hi. I have a question to this entanglement-based networking thing. Can you actually use them for entanglement-based quantum key distribution? Because there you need this maximally entangled state in order to be not having this problem with the trusted repeater thing.
Yeah, sure. Yeah. That's what you sure. If I say I want as a functionality to share a bell state, what I really mean, you share a maximally entangled state in a more or less noiseless way, or as good fidelity as possible. And then you can, of course, use this to all these fancy applications I said at the beginning, including this cryptography thing.
Okay, thanks.
And Matteo, you have a question?
Yeah, hi, can you hear me?
Yeah.
Yeah, hi. I was wondering in the metrics that you show in, I think, a couple of slides ago, where you showed the number of qubits that are required to achieve those entangled states, is it taking into account also the way that those, for example, GHZ states are generated? For example, if I need more qubits to do entanglement swapping to achieve the GHZ states, are those qubits taken into account as storage?
Well, not for the generation, it's just for the storage.
I see.
Because you generate them, and this I don't count. At the moment, at least for what I showed you, this is not taking into account what extra qubits you need at the intermediate level. I'm only showing sort of the qubits for a long time memory, the ones which you need to store eventually, not for building up. It's a different kind of problem, or sort of living in a different phase of the network.
Yeah, great, thanks.
But of course, you have to take this into account eventually as well. Okay, so I don't see any more questions at the moment. So I go on with these genuine quantum networks. So, okay, so rather than doing everything in a classically controlled way, only one thing, one predefined thing or one thing what one agrees on. One really does things now in a coherent superposition. So I try to depict this here with what I said before. From a GHZ state, you can go to either sharing a Bell state between two particles or two others, or other two, so other pairs of particles. And rather than sort of choosing one of these possibilities, you actually do this in a coherent way that you actually share the superposition of all these different possibilities. And for this, you need a quantum control plane. You need sort of a quantum register with different weights and different phases, which actually controls everything which is going on. And well, I put some maths here, but actually that's not so complicated. So you start with a quantum control register, a superposition with certain weights, and then you try that. Then you sort of prepare a state, which is an entangled state, which is shared by all the parties which are involved in the protocol. So everybody now holds sort of the same state, so the sum of all these cases. It's a generalized GHZ state, essentially. So all of the qubits are in 0, all of the qubits are in 1. If you just have two choices in your control register, and everybody shares this state. And now you do all the operations in a controlled way. So for the state preparation, you do some unitary circuit controlled on this register, and you do this at every place. And by doing so, you actually generate, okay, there's one more step, then you can actually erase most of your control register, except at one party. And then you share a superposition of all desired target states with this control register still attached. And then sometimes you may want to get rid of this control register, but I have to say that this is not always possible. In some use cases it is, but it's not generally possible. But that's what you can achieve in general. But okay, that's all nice if the operations are unitary, but what happens if these things which you want to control, they are actually classical themselves, like a measurement? Measurement is actually a classical process. You get some classical data from it. Or sending a photon, that's also a classical process at the end. You use the channel, you send something through. But how can you make all this work also if the processes themselves are classical? And actually, in general, like a measurement, superposed measurement, you want to sort of, measurement is described by PWM, so some positive valued operators, and you have certain outcomes labeled by K, and you want to achieve a certain outcome with certain probability, and then you want to get the target state. And what you want is a superposed measurement would be something where you either do no measurement with certain probability, or you do a measurement and get the outcomes according to this probability distribution. So you either do, so you want to have a coherent superposition of no measurement being performed and getting the sort of a certain outcome in your measurement, and the probability distribution should match by the one just doing the measurement. But if you look at this process, actually it turns out that's a nonlinear process. So this really seems to be impossible. But what you can do is you can mimic the process. You can sort of you can get the same output states by actually always doing the measurement, either on the system you want to do the measurement, or by some auxiliary system which you prepared in a certain state. But you have to know the probabilities of your measurements outcomes for the input state in order that you can sort of prepare the right auxiliary state. If you don't have this information, you cannot do it. But if you have this information, you actually get exactly this desired map. You get exactly this coherent superposition of performing a measurement or not. And actually, this is useful for our purpose, because if we manipulate entangled states, we actually do measurements on entangled states, and they have a probability distribution which is always flat, so equal probabilities. So we know exactly which kind of states we need to put as auxiliary state in order to mimic this. And then we can have something like a controlled sending or controlled teleportation, where you either sort of do a Bell measurement on your qubit you want to send and the part of the Bell state, or you do a Bell measurement on some auxiliary qubit and the plus state. And in both cases, you get a completely random outcome. And what you end up with is then a superposition of the qubit being transmitted through the other side, being teleported. That's the second possibility, or the qubit still being there and just the auxiliary state being destroyed. Okay, in this way you can add quantum control to this teleportation process. And you can also do the same thing with the merging, with the manipulation of graph states, actually with basically everything. And also with the controlled transmission. You can send a photon not just through one path or another path, but you can send it in a coherent superposition of one path and the other path at the same time. And actually people have realized that this allows you to transmit information through channels which each for themselves is useless. It's completely entanglement breaking. But if you have access to both channels at the same time and can sort of send a photon in a coherent superposition through one path or the other and recombine it at the end, then you can actually transmit information. And this is related to things which is sort of this causal order or quantum switch. But actually, you don't need the sort of different time orders, not this sort of artificial thing, but you can do it with real different channels in the real network. Okay, one more thing we can do with these superpositions is, well, actually, rather than preparing a certain target state, you can actually prepare a superposition of different target states. For instance, a GHZ state shared between any set of 3 qubits. So you have GHZ states of size 3, and you don't share between a fixed set, but between any possibilities, any sort of permutation of the 3 parties. And by doing so, actually, you find that if you look at each of the possibilities, at each of the GHZ states, if you do this for a 4-qubit system, if you lose 2 of the particles, all of the entanglement is gone. So the state is completely useless. But if you sort of do this with the superposed state, in this specific way I'm writing here, and if you then lose 2 particles, the remaining state is still entangled. So by preparing this coherent superpositions of different possibilities, sort of not not selecting beforehand which of the 3 parties should share entanglement. By doing so, you can actually protect your quantum states in a better way. And you can also sort of have superpositions of sharing different kinds of states and then deciding later on which of the things you want to use. You can think of really doing a superposition of different error correcting codes of different cryptography protocols. There are many possibilities. We haven't explored all of them, but I think there's really lots of stuff to consider, and maybe things where you get an improvement, a surprising improvement, similar as the thing with the superposed channels and superposed paths. Well, what we did is to use this idea for a thing which is called coherent or randomized benchmarking, which is essentially benchmarking a device or a channel in order to learn when you do some gates. So you say you have some small quantum processor which can do a certain set of gates, and then you want to learn how good are these individual gates actually. And there's a technique which is called randomized benchmarking, where you apply sequences of randomly selected operations, and then you do a certain bunch of measurements specified in certain measurements, and then there's an efficient way of learning the average fidelity of each of these individual gates. By just doing these randomized measurements on sort of circuits of varying size. But unfortunately, this benchmarking, this is limited to certain classes of operations, and sort of to specific groups, Clifford group, for instance. And you have a scaling problem. So if you really want to benchmark larger gate sets operating on not just a single qubit, but on many qubits, this is really scaling badly. So what we said is, well, rather than, let's take our idea from this coherent superposition, rather than sort of doing several independent tests of randomly selected gate circuits. So usually you would select a certain sequence of gates, you would apply this, and then you do some measurement. You repeat this several times for this specific set of gates. And then you select another set of gates and do the same thing again, and yet another set of gates randomly selected. But rather than doing this in this sequential way, you can actually do this in a coherent superposition. So sort of testing all these different gate sets at the same time. And actually what we found is if you do this, it's not only that you get an improved efficiency, so a faster convergence of this procedure, but it's also that you get that you can actually test larger gate sets, actually general gate sets. And the thing is that you can achieve this by having sort of an external device which provides you with this, producing these coherent superpositions, and the gates you test, they are still the same. So that's one use case of these coherent superpositions. Okay, so I'm not sure how well I'm doing this time. I think I'm pretty late already. So maybe this last thing is other protocols I wanted to mention. I just give you 2-3 buzzwords without going into any details. So one thing is about long-range big quantum data transmission. And this has to do with how you realize your long-range communication. And if you do this with the standard repeater, the standard quantum repeater we introduced back in '98, I think, or if you do it with other types of more modern types of repeaters, with encoded or sending encoded information or distributing encoded entangled states. So all these approaches, they scale somehow with the distance, only polynomially or polylogarithmically, but they scale with the distance. What we came up with is a way to avoid this and actually do long-range quantum communication of large amounts of quantum data in such a way that the required resources, they don't scale at all with the distance. So if you count sort of the number of qubits you have actually to transmit through a noisy channel and make a relation to the number of qubits you actually get successfully through, which way you succeed in transmission, then this is approaching a constant. And the key idea behind this is a measurement-based implementation of doing all the operations which are required for error correction or for entanglement purification. There is a trick, which is this measurement-based, what we call measurement-based quantum communication, that you, in order to manipulate a state, you can sort of teleport it through a certain entangled state. And by doing so, you not only transmit the information, but you actually perform a certain operation. Like you perform an encoding operation, you perform a step of an entanglement purification protocol, and what you do is sort of given by the shape or by the type of entangled state you teleport through. And that's the basic trick what we use. And this trick really has the advantage that you get a really good error susceptibility. That is, your resource states, they can be very, very noisy, up to 10% of noise per particle, and still these processes work. Okay, and based on this, you can sort of cook up a quantum communication scheme based on the usage of finite size hashing, and then you really get something with finite size, with a constant scaling in distance. We worked on more entanglement purification protocols using a high-dimensional register to learn information, which actually turned out to be more efficient. That's some recent work which we just published in PRL this year. So if you're interested in this, you can just look up the paper. And the final thing I'm saying is another work where, which is also, I think, like a nice concept, where you can sort of store the information in a quantum network, not in a localized way at individual nodes, but in a delocalized way. That you sort of distribute your information holographically among the whole network. And the advantage of this is that it's better protected. So if some nodes fail, only a small amount of information is destroyed. And on the other hand, it's also that not all the information is accessible. So if you want to sort of store the information in a secure way, such that several parties, or maybe all of them, have to come together and work together to get the information. And if you just have individual parties trying to get it, they just can get some small amount of information. And these two things, this is what you can achieve with this delocalized information storage in this quantum networks. And you can actually do this in a natural way by doing passive protection, not in an active error correction way, but really choosing some sort of encoding where you use decay states or W states, and then you really get sort of a large So little accessible information, and many nodes can fail, and only little of your information is destroyed. And actually, you can generalize this to really come up with networks where you have your information stored in parts of your network, not in a single node, but in a certain subset of nodes, and that you can actually transport it through the network, and then you can localize also the information then at a given node which you choose, or which you can say it should be in a certain region. And all this manipulation can take place by only doing single qubit operations. So it's really a measurement-based thing. Okay, and with this, I'm at the end. I just want to remind you of the two headlines I had. On the one hand, the entanglement-based networks, which sort of shift the challenges to build quantum networks and give you new possibilities and new features. You can optimize networks, you can prepare resource states beforehand, you know what you should prepare. And on the other hand, these genuine quantum networks, where we actually go away from the classical control plane and make everything in these quantum networks genuine quantum, and also have a quantum control plane, and then achieve also some quantum addressing and stuff like this. And the question there is, what else other than these small things I showed you can we do with this additional power? Okay, then thanks for listening, and I'm open for questions. Happy to take some.
Thank you very much for that talk, Wolfgang. So if there are any questions, please ask them. Officially, the meeting time is over, and I do think MeetEcho will kick us out in 10 minutes, but we are open for questions for as long as Wolfgang wants to stay. So Tim, or Rodney, do you have a question since you opened up first, or should I start with the queue?
Video back on to serve as sort of a shadow chair here. Go ahead through the people, but I may have some questions later.
Okay, Tim, would you like to go first?
Yeah, yes, please. Can you hear me?
Yep.
Can you? Yeah, can you? Sorry.
Yes.
Oh yeah, that's great. Yeah, sorry. I have a question about this long-range quantum data transmission. I'm afraid my connection got a bit choppy when you talked about this. I was wondering, you made the claim that there is no scaling with distance, and I was wondering what you meant by this, as in terms of time or in terms of errors?
In terms of resources, which you need to, which are involved. So the scaling of the number of qubits which are involved in total. If you look at the standard repeater schemes, you get some polylog scaling in the distance.
Mm-hmm, mm-hmm.
And also for polynomial L for the standard repeater, and if you take the one of Yang and Lukin, you have a polylog scaling, but the error correction system also has a polylog scaling, but it's really constant. So if you really take this, what I mean here is the involved qubits which I get divided by the qubits I get out at the the reverse thing, sorry.
Yeah, some rate, I see.
I understand. Divided by the ones you have to send.
Yeah,
this
clear.
is really
That's
constant.
Clear. Yeah, thanks.
Okay, and next in the queue is Liang Zhang.
Hi, Wolfgang. Thanks for the very nice talk with a lot of interesting ideas. Yeah, so I really like the part you talk about the genuine quantum network. So I think that one potential application will be related to like a quantum random access memory, which is kind of querying the different addresses in a superposition.
Yes, well, we haven't thought about this, but this really sounds like a good idea to have a look at. Yes.
Yeah. So yeah, I think it will be interesting to extend that to the quantum network context. Yeah.
Mm-hmm.
Yeah. Thank you.
But actually, I have to say, sort of this different time order. So these things of having things in a quantum controlled way, that's not entirely new. I think it's new in the network picture, but people have started discussing this in this context of this temporal order or the quantum switch in different contexts, but not in this quite general terms we try to put this. So I don't claim that we invented the wheel. And I guess also Rodney thought about these kinds of things already a long time ago, at least informally told. But thanks, Lang, for this suggestion.
Yeah.
Any more questions? No, I do have one for myself, which is that, so you showed the scaling of resources, especially for these entanglement-based networks, and you showed that it scaled much better than bell pairs, the on-demand one. What I'm curious about is, have you tried scaling with, have you looked at how it scales with increasing request demand? So as you push the network with more and more demand from end nodes, is the scaling, since the scaling, I'm wondering if, because the scaling with resources is so good, does it also mean that scaling with the number of requests is also just as good?
Well, okay, but we looked at many different scenarios. So we looked at the scenario where you have only very few requests or parallel requests, I have to say. I think that's the important thing. If you only have single requests or a single bell pair in each of the requests, or if you have several multiple bell pairs which you want to share simultaneously. And of course, there's a difference of which kinds of requests you consider there. And of course, the optimal thing you get, or the optimal improvement you get with only very few requests. If each of the requests is just a single bell pair, because rather than having all the possible bell pairs, where each of the parties needs to store n-1 qubits, because it has to store a bell pair between any of the other ones, you can just store a single GHZ state. So that's really sort of very favorable from our perspective. And if you put more and more sort of parallel traffic there, of course, our improvement is going down. And it's also going down if you're taking your probabilities into account. So this is really for this deterministic use. If you really have multiple users, if you say my network should actually be able to provide sort of billions of these bell states simultaneously, then it turns out that at the end of the day, it's best to just store the bell states. But in the regime where you have a smaller number of sort of requested states, there you really get this big improvement. It's well big. It's still only polynomial, but in practical terms, I think this can mean a lot if you really need a quantum memory of just 50 qubits or a quantum memory of several hundred or thousand.
Yeah, so it could be that if you're a network operator, you actually you prepare all these GAZ states ahead of time, and whilst the demand is below a certain threshold, that's how you deal with it, and you save resources. But you would have a fallback mechanism to switch back to bell pairs if it's above a certain threshold, and basically at that point you're just above capacity.
You use this bell pairs then, yes.
Okay, that's interesting. Thank you. Any other questions? Tim, another question?
Yeah, now I'm on. Sorry, yeah, yeah. I found the entanglement-based quantum network is very interesting, but I must say I didn't fully understand the part where you talk about optimization. And my question is. Now, suppose that we completely follow what you propose. Then should we, in practice, perform optimization over purification protocols and protocols to produce GHZ states, etc.? Should this be different from if we follow a quantum network that produces bell pairs on request only?
I would say that if you have different targets, there's a different optimization. And okay, I hear feedback now. I'm looking. This is distracting. Okay, so depending on what you want to produce, you will use a different protocol to generate it. But I'm not worrying about this part at the moment. Of course, you have to build these resource states eventually, and you have to optimize these protocols also. But this is in the first phase, in this sort of build-up phase. What I'm looking at is really, at the end, the storage requirements. I'm only saying, okay, I don't worry how you would generate this. And I think that also for this generalization, there is an improvement. because these states, they might be less entangled, or you have certain or different target states you want to generate, and you can really optimize beforehand how you would use your given physical network to produce just these states. But this optimization is really for the storage. So how much qubits you need to store for longer times, such that you get the desired functionality of the network. This is where we showed this advantage. For the building up of these resource states, this we haven't discussed in this first works. But I expect that also there's an advantage.
Clear. Then that's what I didn't fully understand. Yeah, thanks.
Any last questions? Because I do think Miteko might kick us out. So.
Yeah, I think we'll lose our connection here momentarily, won't we?
Yes, I don't actually know how forceful it is. so
okay.
Either, so if there is there any last question? Final question.
We should thank. We've already lost a few of the participants, but we should thank Wolfgang for this amazing talk. There's such an incredible work going on in Wolfgang's group and in that whole orbit around him.
Yeah. So in that case, with no more questions, I'd like to wrap up. Thank you again, Wolfgang. If there are any follow-up questions, they will be on the mailing list. Not sure if you're on it, but if you're not on it, I'll make sure to relay the questions to you.
No, I'm on the list.
Okay, so Wolfgang's on this. If anybody has any questions, just shoot them at the mailing list so that we can all benefit from the exchange. And with that, I'd like to wrap it up then, and thank everybody else for attending as well. Thank you all.
Well, thanks a lot for listening, for your patience.
Stay safe, everybody.
All right.
I'm going to sign off and go to bed myself.
Cool.
Thanks, Wolfgang.
Okay.
Thanks, Wolfgang.
Okay.
Yeah. Thanks a lot for inviting me.
Yeah, no problem. Thanks, Wolfgang. So I'm also going to disconnect then. Okay.
Bye-bye then.
Bye then.